Thank you, Jimmy, for the wonderful introduction. Can people hear me okay and see me?
That is okay. We can see your slide and we can hear you very clearly. Thank you.
Oh, great. Good morning. It's kind of early. I even don't know how many attendees at the symposium at this time. It's West Coast, definitely very early. But anyhow, still good morning. And I'm going to spend next 25 minutes talking about a topic that we have worked on for more than several years. So the title is called AI for Payment Evaluation and Status and Future. Essentially what we have achieved and what we are doing and what are the prospects in the next few years to 10 years. So I'm going to talk about several subtopics. The first one is the sensor system, 0.5 millimeter 3D laser imaging. We call it PAVE 3D 8K. We designed and developed the sensors ourselves, fully integrated. We're very proud of this achievement. That's the highest resolution at highway speed for pavement survey. And then second one, I'm going to talk about multi-objective deep learning network. How to leverage our experience and know-how developed last 5-6 years to do a multi-objective detection, which is very, very hard. And this research is still in progress. And then we're going to talk about the safety sensor we have completely developed from the ground up using similar 3D triangulation principle, but at substantially higher resolution, 0.1 millimeter for safety evaluation of the surface properties. And then we're going to talk about what the future may lead us. Pavement data collection has 4 major categories: roughness, distress, deflection, and friction. The crown jewel of all these evaluation processes is cracking. Cracking is the dominating factor in pavement surface condition. And the automation of it is very critical, and people have worked on it for decades. So this would be my focus of the presentation. 5-6 years ago, we asked ourselves, we had so much problems in automation of cracking survey, and what is the new approach that we can have better solutions? So we said, everybody switches to deep learning, and that's what we are today. We developed the world first and only production-worthy CrackNet based on deep learning for cracking survey automation. For example, this is a very old, 30 years old illustration in one of my early papers on the system design of automated cracking survey. And then for many of the young audience here, probably you would not know what VHS stands for. And this is the predominant medium that people used for watching movies and sharing visual information about 3 or 4 decades ago. That's prior to that, or along that time, people were using 35 millimeter film as well. And all those information are analog, and they had to be digitized to be analyzed with the computer. So this is an example from 35 millimeter film that was probably captured in the 90s. So roughly 25, 30 years ago by federal highways for one of the LTPP sites. Now, fast forward 30 years later, we came up with this 8K system, which is 100% digital and half a millimeter in resolution transversely. So we cover roughly 14 feet wide of a pavement lane with 8,000 pixels, roughly 4 meter wide. And we can do that at highway speed up to 65. Sometimes we can hit 70 miles an hour. Those are the examples of the systems we delivered to different parts of the world, China, Japan, Europe, definitely in the US as well. We are very proud that the US Army Research Center has received a completed system from us early this year for their research work. Now, I'm showing some visuals to you so you can appreciate what kind of level of resolution we can get. This is about 10 years ago with our prior generation system. And as you can see that we cover the concrete surface, which was highly deteriorated at 65 miles an hour. That's Interstate 35, north of Oklahoma City. Same place, but I zoomed in, and that's the details. Same place, we zoomed in further. That's the details you're able to visualize. Okay, that's the quality of data we were able to get 10 years ago. Right now, we're doing half a millimeter. And this is the visual of actually a street, okay, a concrete street with edges with asphalt materials. As you can see that the faulting information is very obvious in the longitudinal direction. Let me talk about deep learning, how we started and what we can do today. Deep learning is not an analytical process. It is cognition based. So there's no mathematical description of the process other than we develop a network with neurons, artificial neurons, trying to train the neurons to understand our problem. Okay, that's a very conceptual description of what we have achieved. So when you are training a network, it's almost like a training or teaching a child, to read and to do basic math. In this particular case, you have to present materials to learn, and this is the learning set or training data set. We had to label the pavements with cracking information. In this case, those are the red lines. We used about 6 people for a whole year. We labeled about 5,000 to 6,000 pairs of extraordinary high resolution 3D surface images with this type of details. And then we trained the network that we developed and then use the network as the brain to conduct inferencing processing. So this is we call it CrackNet, and we stuck with this name, even though in the last 5-6 years, we went through several iterations. So we worked on pixel level intelligence. For those who worked on deep learning, particularly the CNN type of deep learning imaging processing, the dominating approach or the easiest approach has been using block-based processing, which is very fast and can be very accurate as well. Since our cracking information is very detailed and is pixel-based, so we decided to use a different approach. So we decided to do a pixel-level analysis instead of block, which is very intensive computation-wise, but it worked out actually to our advantage because we can maintain consistency, repeatability, and accuracy. So this is our first generation CrackNet at the pixel level. And we did several follow-up studies we publish papers on each of them. The top one here has been cited over 400 times already. So in the last some years, so we received roughly 100 citations per year on this paper on the pixel level intelligence of CrackNet. So those are the some of the examples. As you can see, the green lines are the actual cracking, and then the pixels with red color or blue color are false positives or false negatives. We're able to do real-time processing. So right now, we actually can drive our data collection vehicle, and at 65 miles an hour, we can produce results as you can see on the screen at that speed. And we're very proud of that. Actually, in office processing, we are at 90 plus miles an hour. Actually, this particular data showing here is a few months old. We are going to do 150 or 200 miles an hour in 2022. As I mentioned earlier in the outline, multi-distresses, right? Cracking is just one of them, which is the most important cracking, distress information, but how to get other distresses at the same time, like people can. That's what we are doing right now. As you can see that we, in a single network, essentially use a single brain to tackle the problems of multiple distresses, multiple types of information. In this case, for example, we have cracks, potholes, patching, sealing, and then we have to identify non-cracking features like marking and manhole, expansion joints, and all those kind of things. Again, how to do that at extraordinarily high speed. This is rigid payments using multi-distress single network. Next, I'm going to address a safety work we're doing, which is very interesting. We finished prototyping of the hardware system, and I'm going to present some of the data analysis we did in the last few months. Pavement safety evaluation, the predominant method today with ASTM standards, AASHTO standards, is based on contact-based, water-based testing, which is limited in length, and it has many repeatability, accuracy problems because the methodology in general contains factors that cannot be properly controlled by the process. For example, the water film thickness, temperature, tire pressure, tire wear, all those are issues that cause accuracy and repeatability problems. This was a couple years ago. We did prototyping for our 0.1 millimeter 3D laser imaging. As we know that microtexture is below 0.5 millimeter. So we are capturing a large amount of microtexture information. Of course, macro texture starts at 0.5 millimeter, which would be included in our 0.1 millimeter sensor system. Here's an example of roughly 200 millimeter square, 200 millimeter by 200 millimeter square on an area. This is an asphalt pavement. As you can see that we are able to visualize extraordinary fine details. I actually identified features as at 0.3 millimeter by itself. The left is a 2D and the right is a 3D. This is another visual we captured a couple years ago. Again, the left is a 2D, the right is a 3D representation of the same surface of 200 millimeter by 200 millimeter. So essentially what we like to do is we'd like to capture most of the micro texture information and also all the macro texture information in a single sensor at highway speed, so we can analyze the visual information for texture information, so that we can not only reproduce ASTM MPD texture information, but also we can correlate our data with friction testers. So I'm not going to read through all the text, but I'm going to show you some visuals. Those are the devices we're using. The top 4 types of devices are commercially available. Some of them actually are ASTM standard devices. And then the bottom one is our own 0.1 millimeter 3D. Those are the visuals. You can see the 2D and 3D on asphalt pavements and also on concrete pavements. So we can get extraordinary details. And then here, as you can see, those are ASTM MPD index. We are comparing our safety sensor, which is in the dark bars, versus LS40, which is a static 0.05 millimeter 3D device, but it's a static. You essentially put the device on the pavement to take a scan, and we have a very good correlation there at both low speed and high speed. And then we also develop a neural network to estimate the actual friction value versus dynamic friction tester, which is a standard device used worldwide. As you can see, our neural net prediction produced 0.84 R-square value, which is very good in our business. Grip tester comparison, we can achieve a much better result than the shotgun result we got from traditional linear regression, which is very, very poor. We also can use that to do hydroplaning estimation, which is very, very important for pavement safety under raining weather. And those are the hydroplaning estimations for certain sections of pavements with different treatments. So I have a couple more slides finished. I hope I'm on time. The 0.1 millimeter 3D safety sensor generally can generate comparable MPD results. And we also can use neural net models to achieve high accuracy in friction prediction, comparing with traditional standard friction testers. And we also can estimate hydroplaning speeds on different pavement sections using our safety sensor. All right, so another thing we're doing is deflection measurement for pavement. So as we know, FWD has been the worldwide standard for the last few decades, and how to leverage 3D laser imaging to do that. And we have different approaches. This is just one of the methods we are investigating. We are hoping to start this type of research next year, which would require a big truck with a standard axle loading to do that. But it's very fascinating just because the hardware and software technologies are coming together very well, so we can use them for our advantage. People probably heard of self-learning. In this particular case, there's a new technique called generative adversarial networks called GANs, which has been very popular in the last 4 or 5 years. It was invented about 4 or 5 years ago and became widely used as a research tool. I think we're going to use that. As I mentioned earlier in my presentation, training is very costly, and how to do self-training. If we can get it work, it's going to save lots of time and manpower. I'm not going to talk about too much about metaverse, but it's something that's happening right now. I think in the next 5 years, we can see industrial use, and in 10 years, I think it's going to be more common than just a concept today. Anyhow, I'm not going to read my conclusions. Essentially, sensing technology and hardware platforms and also software platforms are getting very mature in other industries, and we are very fortunate at a time that those underlying technologies are getting mature and we can apply them to payment surveys. It's not easy. I worked on this in this area for 25 years, and it's still challenging in certain aspects. So we are hoping to make more progresses in the next few years. So I have to thank all the agencies and the people who supported our work in the last 2 or 3 decades, and very appreciated. That's the end of my presentation, and I look forward to getting any questions.
Well, thank you very much, Professor Wang. It was an excellent and informative presentation. We have time for a couple of questions from the audience. You can type your questions in the Q&A slot or simply unmute yourself if you have any questions. Please.
Hi, this is Xiaoming, and Professor Wang, a very intriguing presentation. Thank you. And so where do you see the future go, I guess, with the increased capability of computing, I mean, supercomputing almost, and also maybe autonomous vehicles, how these new technologies benefit pavement evaluation?
Well, we right now, as mentioned, there are 4 categories of payment evaluation. The industry as a whole, including ourselves, has solved largely the problems of longitudinal profiling, and we probably 80%, 90% on the full automation of distress automation. So for deflection, we are still in a stone age. FWD was invented in the 60s and 70s, and people started using them in the 90s. You know, 5 decades later, we're still using it. So that's it's changing. We have technologies that can do high speed today. How mature they are, how reliable they are, we don't know. And then safety evaluation is a similar situation. Essentially, is a half-century exercise that has never changed. So I think in the next 5, 10 years, we should see truly high-speed, reliable deflection measurement device, a non-contact for sure, and also same thing with safety evaluation. Next 5, 10 years will be a golden age for the researchers. Autonomous driving, I stayed away with it because those guys have so many people and so much money. Essentially for everything we want to do, they can do in a flash of a second, right? They have literally, there are 1 million people. I'm talking about 1 million staff members worldwide with $1 trillion assets, with those dozens of companies working in autonomous driving, which is just like literally 1,000 or 10,000 times more powerful in people and assets and money. So I hope we can get involved with those guys. They can pay attention to us, but they don't. Yeah, a lot of people tried to get Google involved 10-some years ago. They had no interest. Anything less than $1 billion, they have zero interest. And that's what our industry is. Payment survey definitely is a sub-$1 billion industry. So, but, you know, again, you know, those big guys don't get in. So what happens? University researchers and small businesses have lots of opportunities because we are in a narrow niche. And for us, it's a big area for infrastructure, transportation infrastructure evaluation. It's a big area. It's very important.
Thank you. We have more questions, Professor Xu.
So yeah, I was gonna ask, like, you know, with the changes in pavement design, for instance, if we're dealing with pervious pavement versus the traditional impervious pavement, would that affect your algorithm?
Pavement design, the new ME design uses a lot of distress information. The 93 design guide doesn't. So that actually is a big motivation, the payment industry by itself, how to produce a comparable cracking protocols so people can collect the data and analyze the data and produce results in a consistent way. So for example, Washington DOT, Oklahoma DOT, Caltrans, those cracking information are comparable. Right now, we are not. So I'm actually finished a phase 1 project for NCHRP to define cracking standards. And there's a new project, RFP is out, so we'll be competing for that as well. So how to define an implementable cracking protocol that can satisfy both payment design at project level and network level, there's PMS needs. And so covering essentially the entire spectrum of payment engineering. It always sounds very simple, but it's been taking decades and decades of work with many teams. We still got stuck. So I think that it's a very, payment design side, they're going to rely more on distress information, which is good. But again, if the data is not good, the entire process is not good. But we are trying very hard, our team and other people in the industry in recent years to improve data quality, both from the data collection side and also to the analysis side.
Thank you. That's all my questions.
Thank you. We have a question from the audience. Just 1 minute. The question is for a pavement condition assessment. What are typical cost per lane mile for generating important results?
Oh, what's the cost? The cost is, this actually is a very relevant question to a payment survey. Just because people charge $1 a mile doesn't mean they can produce the results. So this thing has to stop, just because a lot of people came into this industry, say, you're charging like $100 a mile, I can do $50. The third guy said, I can do $10. The fourth guy said, I can do $1. That's what's happening in the last few decades, right? When you have this kind of cost spiraling down, then the industry had no funds to do R&D. So essentially, they use very poor quality equipment to do data collection and producing very bad results. And so this has to stop because it's a public asset. We have trillions of dollars, even though we are not in the autonomous driving area, but if you look at the payments, we literally have trillions of assets. That's public money. And how to monitor this asset, we have to use the best tools we can get, even though it can cost a little bit more. That's how people can use the margin to do R&D, right? If you look at the industry as a whole, there's no R&D in the private sector. And I am the only remaining people that's been doing innovations in hardware and software solutions. The reason being is the private sector cannot make money. So the cost varies a lot. So I don't have I actually do not do service work myself. I'm a researcher, but my understanding from the industry is it used to be a few $100s a mile. It came down to 200, 150. I'm not sure if people are doing less than $50 a mile. People can do that if the clients, which would be the public agencies, if they don't care, the cost is going to come down furthermore just because they just want to satisfy federal mandates to get data, and they don't care about the quality of the data. They don't use the data. So this kind of culture has to change.
That's correct. It looks like we have one more question from Professor Yu.
Yes, thank you, Timmy. Good morning, Kevin. Thanks for a very visionary talk. I think this is the future of a profession should build upon with more advanced technology based on the advanced research. Yeah, actually, I'm going to share some observation. For example, in my individual discussion with engineers at Ohio Department of Transportation, they were in the similar status like you described. Maybe there's some mandates, they just recruit some companies, connect a lot of data, or they said they don't know to do anything or what to do with a lot of data they connected. Maybe one barrier, like I think they did a comparison study. They have the engineers make subject to rating of road condition, and then they compare with the rating based on the data, like technology that scan the road, they see a big difference. So essentially, they don't have some psychology repulsion or technology acceptance. Because engineers now come up with the data come up with a conclusion that's different from the engineers what they will come up with based on their experience. So that maybe also leads to some reluctance to accept the technology. So what's your perspective about what can be done to overcome these kind of barriers?
Yes, this is a very good question. It faces all the agencies. People don't trust the data because they cannot have, it's like 1 + 1 = 2, right? But when you do cracking surveys, it's not. It's like the results are all over the board and it's like random numbers sometimes. Then they stop. They said, why am I spending millions of dollars into this? Or why am I spending $500 a mile? I give you $5, just go away, like this type of thing. So it's a very good question. And actually, we are at a stage on the data collection side, things are coming together to be very mature and very standardized on the data side right now. 10 years ago, not everybody's doing different. So we can get 1 mm resolutions, largely speaking. Now the coming up process is defining what a cracking is and how to actually compute the cracking information into a value that people say this is good, this is poor, or this is something between, and how we can use the results of the analysis for both design and payment management. And so there's a lot of work going on right now. Federal Highway has a proof-of study that has awarded probably about 10 projects already in the last 5 years. And the NCHRP has new projects coming up. One of them is the second stage to finalize the cracking definition to become an AASHTO standard. And we'll be very much involved in that process, hopefully. So I think it's coming along, but it will take a lot of education and also cultural change for the industry. I'm talking about the agencies and industry, private industry, and university people to come together and really do something like they did for International Roughness Index. In the 90s, people were starting using it, and 30 years later, we're still doing research. But IRI is more accepted than anything else today as a standard to measure longitudinal roughness. Cracking is 10 times more complex. So I'm hoping next few years, people will come to a conclusion, probably within 10 years, right? That we are very close to a consensus industry-wise. Everything should be done this way, and everything is accepted as a standard. People actually practice based on the standards. So those will come along in the next 10 years, I hope.
Thank you very much.
Right, Dr. Wang, we have one more question, but we have only 1 minute. So please make it quick. This is about computing power. The question is, are there ways to help speed up a rate for data processing? 1 minute, please.
Well, all those questions are so good. I did not have time to talk about them. Computing. So that's why university is so important. You cannot expect the private industry in payment industry and all the agencies to do it, even to start, to be honest. We use a very high-powered GPU to do it, okay? And if we use a CPU, we have to bring a generator to the vehicle and put like 4 or 10 Intel Xeon processors to run it. We use a very powerful GPU, which literally has 4,000 processors and then the neurons are built into those GPUs. So
10 seconds, please.
Yes, so GPU and getting people, getting graduate students interested in computing, hopefully with civil engineering background to do coding, to learn hardware. You need a multifaceted background to do this kind of research. Thank you.